This is the sixth part of a series on mass timber construction, in which this has been a cooperative effort between ICC and the American Wood Council. And in this particular segment, we're going to be discussing fire design and connection protection, and also special inspections, and then we'll throw in a few additional topics, including acoustics, or sound transmission, that is, and energy towards the end. As Marcy mentioned, I'm Jason Smart, Manager of Engineering Technology with AWC, and then we also have my colleague Lauren Ross. He's the Manager of Engineering Research at the American Wood Council here. He's going to be the one presenting on energy later on. So, and like I said, in addition to the topics that are listed here on this slide, it doesn't mention it, but we'll also be talking about sound transmission and energy. All right, Marcy already covered this slide a few minutes ago, disclaimer, so I won't belabor it here. I do want to mention that certificates of completion are available upon request for continuing education credits following this webinar. And also this course is registered for continuing professional education credits with the AIA, American Institute of Architects. For AIA members, credits earned on completion of this course will be reported to AIA. And please note that this presentation is copyrighted and reproduction without permission is prohibited. All right, here's the basic course description. I think you've already seen this when you registered for the course, so we'll skip right to the learning objectives. Yeah, over the next 90 minutes or so, my goal is to help you with the items listed here, these 4 areas. First, understand the basic code provisions relating to the new mass timber construction types. And then we'll learn about code provisions relating to the design of fire protection on mass timber connections. And also I want you to become familiar with special inspection requirements for the new tall mass timber construction types, and then also we'll explore various options for acoustics and energy performance, like I mentioned. All right, so we have the first poll question here, and that's just to find out a little bit about our audience makeup. Marcy, will you administer that? Marcy, we can't hear you right now. If you're talking, you might be muted. There we go.
There we go. Sorry, all my buttons kind of disappeared for a minute.
Oh, okay. All right.
All right, and I usually wait until about 80% have voted, or 30 seconds. I'm pretty close to that 80%, so there we go. Let me close and share. So we have 55%, let's see, 55% engineer, 30% code official, 7% architects, 3% builders, other manufacturers or other, and 4% fire service. No matter your profession, we are delighted that you're here and hope that you find something of value.
Yep, indeed. All right. So let's get started on the meat of this. And the first topic that we're covering today is, like I mentioned, fire resistance design provisions for the new mass timber construction types. Here's the updated IBC Table 601. That's what I'm going to start off with, that because I'm sure most of you are familiar with, especially you designers out there are familiar with Table 601 of the IBC. The highlighted cells here, yellow highlighted cells, are the, or columns I should say, are the new ones. Those are for the 3 new types of construction. And notice that the fire resistance rating requirements for type 4A are the same as those for type 1A. And then likewise, both 4B and 4C have the same fire resistance rating requirements as 1B. All right, Now let's back up and look at some even more basic and more generally applicable principles related to fire safety, specifically in the context of the IBC. Non-combustibility and fire resistance are two very different things. I want to impress that upon everyone here. They each have their place in the code, and the code requires non-combustible materials for some purposes and then specific fire resistance ratings for others. So they're both very important concepts, but they are not, they're very different concepts in terms of fire safety. Some non-combustible building elements have little or no fire resistance because although they may not burn, they still lose their strength rapidly upon being exposed to fire. Conversely, you can have a combustible building element, such as a large cross-section wood beam or a wood frame wall that has membrane protection, such as from a gypsum wallboard, for example, that has comparatively higher fire resistance. Large cross-section timber elements have inherent fire resistance, even when exposed, owing to the strength that is retained within the relatively cool core and the insulative protection provided by the char that's surrounding it. So these mass timber elements can be designed to provide a prescribed level of fire resistance as either exposed members or with the added help of non-combustible protection applied to them. And we'll get into much greater detail on that concept in just a little bit. Although most of the members and assemblies in traditional heavy timber construction, now called Type 4 HT, are not required to have specific fire resistance ratings, they do have an inherent fire resistance due to the fact that they're required to have minimum cross-sectional dimensions. These minimum cross-sectional dimensions are specified in IBC section 2304.11, and they're based on tried and true track records of performance over the past century or even more. Of course, this represents a very different approach to the manner in which members and assemblies in the new types 4A, 4B, and 4C construction are designed. That's different, that is, but not necessarily better or worse. In the new types of mass timber construction, the members and assemblies must be designed to achieve certain prescribed fire resistance ratings, like the ones I showed you in IBC Table 601 a few slides back. Although they still need to meet the requirements of IBC section 2304.11, that's the minimum dimensions, these minimum dimensions may actually need to be exceeded in order to meet the prescribed minimum fire resistance ratings. So, and that's especially the case in types 4B and 4C construction on mass timber surfaces where there is no non-combustible protection. As you can see from IBC section 722.7, which is shown here on this slide, the first section or the first sentence is referring to the general options for establishing the fire resistance of any member or assembly. Section 703.2 deals with testing to the ASTM E119 standard, and section 703.3 lists the other alternatives for establishing fire resistance that are already in the code. These options include fire resistance designs and approved sources, calculation methods, and engineering analysis based on comparisons to tested assemblies. One primary premise for types 4A and 4B construction and their associated building heights is that these buildings should be able to withstand, until burnout, a contents fire that is not controlled by sprinklers or by firefighters. This is a very conservative approach because, of course, these buildings would be required by code to have sprinklers, and typically there would be a fire service response. But in order to achieve this conservative design objective, the non-combustible protection that is required in types 4A and 4B construction plays a particularly important role. Specifically, it not only increases the fire resistance rating of the mass timber elements to which it is applied, but it also prevents or delays involvement of the protected surfaces. This can allow time for the combustible contents, like furnishings, for example, to be consumed and burn out before the protected mass timber ever becomes involved in the fire. And by being involved, that means it's being consumed and contributing to the heat release of the fire. On these protected surfaces in types 4A and 4B construction, the non-combustible protection is required to provide at least 2/3 of the fire resistance required for the element or assembly. And the code is explicit about how the fire resistance is determined. It's simply the summation of the fire resistance attributable to the non-combustible protection plus the calculated fire resistance of the mass timber element itself. The code assigns values for these non-combustible protection contributions, which are then added to the calculated fire resistance rating of the wood member. The tables used in this prescriptive approach are shown here in this slide. Of course, these tables are new to the IBC and they're very simple. You have a rating, and in accordance with the 2/3 principle that I just mentioned, you have a minimum level of protection that must be provided by the non-combustible protection. And you have table 722.7.1 parent 2, which is the table shown here at the bottom that indicates a prescriptive amount of fire protection that can be assumed to be attributed to the in this case gypsum or whatever non-combustible protection you have. You can see that 1/2 inch type X gypsum board, for example, is assigned a contribution time of 25 minutes, and 5/8 inch type X is assigned 40 minutes. The non-combustible protection values provided in this table are on a per layer basis, and they are additive for multiple layers of gypsum board. So in this manner, you can achieve 120 minutes of non-combustible protection by using 3 layers of 5/8 inch type X. Now, there are cases where these tables are necessary even in type 4C. If you've attended any of the other webinars in this series previous to this, you'll recall that shafts and exit enclosures require a minimum of 40 minutes of non-combustible protection on mass timber surfaces. And that's part of their required fire resistance rating. The code recognizes 7 methods for establishing fire resistance. Any of these 7 methods can be applied to any construction type, whether fire resistance ratings are required or not, and wherever fire resistance ratings are required. They're all based on the same standardized testing. They're all based on the same standardized exposure, I should say, and that is the same exposure that is described in the standard test, ASTM E119. But as you can see from this list, a member or assembly does not necessarily have to be individually tested to be recognized by the code as having a fire resistance rating. Of the 7 recognized methods for determining a fire resistance rating, the one I have listed in red here on this slide is the one that we're going to talk about next. Specifically, I'm referring to the calculation methods that are described in IBC section 722. IBC section 722.1 references chapter 16 of the NDS, the National Design Specification for Wood Construction. And that's for calculating the fire resistance rating of exposed wood members and wood decking. And then AWC's Technical Report 10, which I'll call TR10 from now on, provides background and examples on performing the actual calculations that are specified within Chapter 16 of the NDS. TR10 and Chapter 16 of the NDS deal with the same methodology. It's a mechanics-based methodology, which I'll describe in more detail a little later. In fact, Chapter 16 of the NDS is based on the methodology presented in TR10. However, TR10 goes into a lot more detail, and it gives significantly more guidance in the NDS, so it's a great resource for designers who want to fully understand the provisions of the NDS and show compliance with them. Here's the actual code language from IBC section 722.1, which deals with the calculated fire resistance. As you can see in the highlighted portion here, Chapter 16 of the NDS is the reference standard that's given for calculation of fire resistance for exposed wood members and wood decking. So this chapter, chapter 16 of the NDS, allows the fire design of exposed wood members for fire resistance ratings up to 2 hours. It applies to any exposed wood member, including those in beams, columns, wall assemblies, floor ceiling assemblies, and roof ceiling assemblies. For decades now, the NDS has addressed fire design of traditional heavy timber members that were already included within its scope. These materials include sawn lumber, glued laminated timber, and structural composite lumber such as LVL, PSL, and LSL. But then also, for the first time in the 2015 edition, the NDS was expanded to address cross-laminated timber, or CLT. And of course, because of this, Chapter 16 now addresses fire design of CLT as well, along with the other wood products that are listed here. And then TR10 has also gone through some recent updates in order to support and provide background for the changes to the NDS, and also the commiserate changes to the code itself. TR10 has always provided the history, technical justification, and expanded details and commentary on this code recognized mechanics-based method. However, the most recent edition of TR10 now also addresses not only the design of exposed wood members, but also provides empirical database design guidance on design of protected wood members. This guidance and the E119 test data behind it served as the basis for the non-combustible protection provisions that are now included within the 2021 IBC. And it pertains, as it pertains to the new mass timber construction types, that is. So I want you to note that that TR10 provides guidance for design of both combustible and non-combustible protection. An example of combustible protection would be additional wood cover added to the protected wood member, whereas an example of non-combustible protection would be a gypsum board applied to the protected wood member. That's just an example. Of course, there are other possibilities as well for non-combustible. That's probably the most common though, gypsum board. These provisions for design of fire protection, both combustible protection and non-combustible protection, allow for designs that go beyond the 2-hour fire resistance rating limit that I just mentioned and on the last slide, because that 2-hour limit is applicable to the exposed wood members. So anything added, any additional fire resistance gained from non-combustible protection applied over that can go beyond that 2-hour limit. All right, so we have our first, this is poll question number 2, our first quiz question. Marcy, you want to administer this one?
Sure. So fire resistance and non-combustibility express essentially the same concept in fire safety. Is that true or false? And I think most everybody's got this. So,
good.
So I've got 70%, and we've got a lot to cover, so I'm going to share it. 83% say false, 17% say true. What do you think?
Good. Yeah, it is false. They are very different concepts, non-combustibility versus fire resistance. That's better than the 78% that we got on the morning session. So I guess this group is listening a little better, just a little bit. All right. Now, let's briefly go through some of the basic physics and principles behind the calculated fire resistance of exposed wood. First off, wood has a fairly low thermal conductivity. In other words, it's a good thermal insulator. And this is true both of the uncharred wood in the center of the cross section, and then also the charred layer of wood surrounding it, that's shown in this depiction here. And then also from a thermal expansion and contraction standpoint, wood is relatively dimensionally stable compared to other building materials. Wood chars at a predictable and easily modeled rate, which allows for accurate estimation of section loss at a given time under a standard fire exposure. And since the since wood and the surrounding char layer are such good insulators, the wood core beneath the relatively thin heated zone in a heavy timber member remains cool, or at or near ambient conditions. Because of this, the core of the heavy timber member retains its strength. This is a graphic representation of the concept behind the mechanics-based calculation of fire resistance for wood members. This diagram shows the idealized section loss of a wood beam with fire exposure on 3 sides. The capital B and capital D in this diagram represent the initial breadth and depth of the beam cross-section, that is before being exposed to fire. And then the lowercase b and d represent the remaining breadth and depth of the section beneath the char layer after a given fire exposure time. Note that in this example, the top side of the beam is not exposed to fire. It's depicted as supporting what might be a floor ceiling assembly, for example. And in this manner, that top side is protected, so it's not losing section. Let me back up. One point I wanted to make is that this 3-sided exposure scenario may also apply to, say, a column that is up against a rated wall assembly if one side of the column is protected. So I was using the example of a beam here for 3-sided exposure, but it may sometimes, it's most commonly probably used for beams, but beams supporting a floor ceiling assembly, but it could also apply to a column. And then this is the similar graphic showing the idealized section loss on a column or it could be a beam that doesn't have a direct, it's not in direct contact with the floor ceiling assembly when it's exposed on all 4 sides. Although the remaining uncharred section of wood is represented by the lowercase b and d here, the actual mechanics-based design is actually a dimension less than what you see depicted as lowercase b and lowercase d here. Now, this additional reduction in the assumed remaining section accounts for strength reductions in the relatively thin heated zone at the interface of the char layer and the underlying wood. This heated zone is shown here in this depiction as a deep red ring around the cool core of the wood member. So the additional reduction also accounts for rounding at the corners, although the effect of this rounding is relatively minor compared to that of the heated zone. All right, the table in this slide is taken from NDS Chapter 16. It provides a quick design reference for determining the char depth at a given exposure time. Those are the values you see in the middle column here. And then the char depths are given in inches for corresponding fire resistance times of 1 hour, 1.5 hours, and 2 hours. And then the column on the right provides values of effective char depth, or A sub EFF. Notice that these values are about 20% greater than the values in the middle column. This additional 20% increase in the assumed char depth provides the further reduction in section properties that I referred to on the previous slide. Again, this accounts for strength loss in the heated zone and rounding at the corners to a certain extent. So the fire design of exposed wood members is based on effective char depth rather than a char. But there are some design applications that use values that are in the middle column, the char depth, not the effective char depth, and that's primarily used for protection, say like protection for connections, which I'll talk about in the next portion of this presentation. All right, the table that I showed on the last slide provided char depths and effective char depths for wood products other than CLT. Now let's talk about the char depth model specified for CLT within the NDS. This is different from the model that's used for all the other wood members or wood product types. This difference acknowledges a phenomenon in which a portion of the protective char layer is lost when the char front reaches a glue line. And here are the char depth values resulting from this model. This table, which also comes from NDS Chapter 16, provides effective char depths for CLT with various lamination thicknesses. The table applies only to CLT in which all of the laminations in the layup are of equal thickness. But the NDS commentary also has provisions for fire design of CLT with laminations of unequal thicknesses. It provides a separate equation that can be used as more versatile. It's not quite as simplified, and it can be used for other CLT layups that have different lamination thicknesses through the cross section. That's not quite as common, at least not here in the US, so that's why this primary design guidance is just based on the assumption of equal lamination thicknesses. Notice that the effective char depth values in this table are generally greater than the values given in the NDS table that I showed previously for other wood members. Now, this is not because CLT has a different nominal char rate. In fact, it is assigned the same nominal char rate as the other wood member types. Rather, the difference is because of the different char depth models that are used. Like I said, CLT has a different char depth model. Also note that CLT with thinner laminations has a greater effective char depth at a given fire resistance time than CLT with greater lamination thicknesses. This also is a result of the model for CLT char depth. So using this CLT model, a thickness of CLT equal to the effective char depth is subtracted from the exposed surface in a manner that's similar to the procedure used for design of other wood members. However, unlike other wood members, the cross-section of CLT has distinctive orthogonally oriented layers, and this has to be accounted for in the mechanics-based design or fire design. So there is some good guidance given in TR10, especially in example 4.6 of TR10, to provide details on how this can be handled, how this type of mechanics-based design can be handled for fire design of CLT. But then there's also a simplified method for design of CLT, which is outlined here on this slide. For a 5-layer CLT having 1.5-inch thick laminations, as shown in this example, the fire design could conservatively be based on the design properties for a 3-layer CLT made of the same lamination types and thicknesses. That is, provided the effective char depth doesn't exceed the thickness of the 2 neglected laminations, which is 3 inches in this case. So this simplified methodology would work. It'd be conservative for both a 1-hour and a 1.5-hour fire resistance rating in this particular example. All right, so far we've touched on the fire resistance design and calculations for exposed mass timber. And for the most part, these procedures remain unchanged from previous editions of the NDS. Using this mechanics-based method, the 2 main variables that determine the fire resistance of an exposed wood member are firstly the cross-sectional dimensions of the wood member, and that's why larger members tend to have greater fire resistance. And then secondly, the ratio of the actual design load on the member to the full ASD load, allowable stress design load. This second variable is known as the load ratio. And if the load ratio on the wood member is decreased to a ratio less than 100% of ASD, the result will be an increase in fire resistance. And this is due to the fact that a smaller load ratio would not require as large of a remaining section to continue supporting the load, and therefore it would accommodate greater section loss and hence a longer exposure time to fire. All right, at this point, I wanted to remind you that when it comes to the fire resistance requirements for the 3 new types of mass timber construction, you can combine the calculated fire resistance of the wood member itself with the added fire resistance of any non-combustible protection that may be applied to the surface of the wood. This is a very important point. It's one of the characteristics that distinguishes the fire design of wood from that of other construction materials. For wood, you can rely on a calculated amount of inherent fire resistance from the member itself, and then, if necessary, add to that any additional amount of protection that may be prescriptively required or necessary to achieve a particular fire resistance rating. And just so that we're clear, the inherent fire resistance of the wood member itself is calculated in the same manner that we've been discussing so far as the way that you would calculate fire resistance of an exposed wood member. As an example, consider a building with CLT walls and floors, like the one shown in the picture here on the left. Say the CLT alone has been calculated to have an inherent fire resistance of not less than 40 minutes based on its thickness and design load ratio. In order to achieve a 2-hour fire resistance rating, the designer could simply specify 2 layers of 5/8 inch type X gypsum board on the walls and on the ceiling to provide the additional 80 minutes of fire resistance necessary in order to achieve the full 2-hour rating. As we discussed earlier, the 2021 IBC prescriptively recognizes the contribution of 5/8 inch type X gypsum board as being 40 minutes per layer. So that's 2 layers, 80 minutes. And this would not only achieve a minimum fire resistance rating of 2 hours, but for type 4B, it would also meet the prescriptive requirement of having not less than 2/3 of the required fire resistance rating coming from non-combustible protection. Now in type 4C, there is no requirement for any of the fire resistance rating to come from non-combustible protection. In this case, if the designer chooses not to use any gypsum, any non-combustible protection, he or she would need to design the CLT itself to provide the full 2 hours of fire resistance. And I wanted to point out that if this option is taken in the design of it, this may necessitate the use of a thicker CLT in order to achieve the required fire resistance rating without any non-combustible protection. The calculated fire resistance of timber decks, including nail laminated timber or NLT, can be calculated using section 16.2.5 of the NDS. The provisions of 16.2.5 apply to timber decks consisting of planks that are at least 2 inches thick. Now that's actual thickness, not nominal thickness. The planks are required to span the distance between the supports, and under this section, single and double tongue and groove decking are designed as an assembly of wood beams fully exposed on one surface only. That's the surface facing towards the fire, or the exposed surface. Butt jointed decking, on the other hand, is designed as an assembly of wood beams fully exposed on the bottom, and then also, in addition to that, partially exposed on the sides of each lamination. To compute the effects of partial exposure on the sides of each lamination, the char rate for this limited exposure is taken as 1/3 of the effective char rate. For butt jointed timber decking, which includes NLT, these calculation procedures do not address thermal separation. However, thermal separation can be addressed by other means, such as the addition of layers which provide a known amount of thermal separation on the ceiling and or the floor surface. Examples include gypsum board on the ceiling and a wood structural panel or cast in place topping on the floor side to provide thermal separation. Also wanted to note that cast in place toppings do have benefits when it comes to sound transmission as well, which we'll talk about later on. Now, as for glued laminated timber, these typically have stronger laminations at the top and bottom when compared to the laminations closer to the neutral axis. Because of this, additional tension laminations are required to replace interior core laminations so that the extreme fiber remaining on the reduced section will have adequate strength at a given fire resistance time, or at a given exposure time. This is a detailing provision that requires communication and coordination between those responsible for the fire resistance design and those who are responsible for the structural design. On this slide, you can see an excerpt from NDS section 16.2.4. The provisions requiring this lamination substitution are highlighted here. Before we get deeper into the actual fire resistance design of glulam beams, I wanted to just kind of define briefly what we mean by balanced versus unbalanced for those who don't know. It's a pretty simple concept. Basically, it's just balanced layups are those which have symmetrical layups of laminations about the center line, whereas unbalanced do not. And the reason why I wanted to point that out is because we use that term in the next slide, because that affects the provisions, fire design provisions relating to glulams. Excuse me. This figure is taken from AWC's TR10. It shows how those core laminations are substituted in an unbalanced beam. As you can see, the number of core laminations that need to be substituted depends on the required fire resistance rating. A 1 hour rating only requires the substitution of 1 core lamination, whereas 1.5 or 2 hour rating requires substitution of 2 core laminations. And these particular layups would only work for glulam members with 3-sided exposure. An example of this would be where one edge is completely protected by a floor system on the top edge, like I mentioned earlier. And then this figure, also taken from AWC's TR10, shows how those core laminations would be substituted for a balanced beam scenario. These substitutions shown here on this slide can be used for either 3- or 4-sided exposure. All right, so we have another poll question. Marcy, you want to ask this one?
Absolutely, indeed we do. So one code recognized method for calculating the fire resistance rating of exposed wood members and decking is NDS Chapter 16. True or false? Wow. Hopefully this wasn't too easy for people. Okay, I've got almost 30 seconds here. Let's close it. And 94% say true. Please tell me that that's the right answer.
Yeah, it is. Yeah, and I guess that's good that I repeated that several times. Probably most of them would have known that anyway. So, yep, very good. Yeah, NDS Chapter 16 is referenced, like I said, in IBC Section 722 as one of those code recognized methods. All right, so let's move on to the next section here of our presentation. We're going to talk about how to design fire protection for mass timber connections. As I mentioned previously, in these new types of mass timber construction, types 4A, B, and C, fire resistance ratings are required for most of the structural elements. This is one of the things that makes these new mass timber construction types very different from traditional heavy timber construction. And it necessitates a totally different approach when it comes to the connections. Wherever structural members or assemblies are required to be fire resistance rated, the code requires the connections between those members or assemblies to have an equal level of fire resistance. Unlike for timber members, which are required to have, or which are recognized to have an inherent level of fire resistance on their own, connections are required to be protected. In other words, 100% of the required fire resistance for a connection must come from protection applied over the connection rather than from the connection itself. So while the connection shown in the photo on this slide would be acceptable in type 4HT, or traditional heavy timber construction, it would not comply with the prescriptive provisions for types 4A, 4B, and 4C construction without protection being added to it, additional protection being added over it. All right, these are two excerpts from the code sections which require protection of connections between structural members of the primary structural frame. Specifically, these requirements are found in IBC sections 704.2 and 704.3. As you can see, the code requires such structural connections to be protected on all sides. And you may recall from a previous slide showing an excerpt of IBC table 601 that these primary structural framing members are required to have a 3-hour fire resistance rating in type 4A construction and a 2-hour fire resistance rating in types 4B and 4C construction. Here's an excerpt of the IBC provisions dealing with fire protection of connections. As you can see, two options are provided. The first option is to perform a standard ASTM E119 fire test, in which the connection is included within the tested assembly. And if this option is taken, just like for any standard fire test, the connection would need to be loaded during the test. And then the second option is the engineering analysis option. The design objective in such an analysis is that the average temperature rise at the interface between the protection and the connection itself must be limited to an average of 250 degrees Fahrenheit. Now that's a temperature rise, that's not the absolute temperature. So that means that average temperature at that interface can't rise more than 250 degrees. Notice that the last sentence of item 2 clearly defines the connection as including the connection hardware, fasteners, and portions of the wood members included in the design of the connection. This is an important point because it means that the connected wood members themselves cannot be used as part of the connection protection unless those members are intentionally oversized for this purpose. Generally speaking, the connection protection is made up of distinct members of either wood, gypsum, or some other approved material that is applied over the connection. With regards to option 1, the testing option, this can be useful in certain circumstances, especially for unusual connection designs involving proprietary components. But obviously it would be impractical to test every connection configuration this way. This is where the second option, the engineering analysis option, provides a more practical solution for everyday designs. NDS section 16.3 provides the requirements for the manner in which connections are to be protected. Connections that are between members, which are required to be fire resistance rated, must be protected from the fire exposure. This protection can be provided either by first additional wood cover beyond just the wood member that's part of the design of the connection itself, or fire rated gypsum board, such as Type X gypsum board, or some other approved material for which the required fire protection time is demonstrated. And then also another option is that you can use any combination of those three options above, the options listed there. And again, just like for member design, TR10 provides detailed guidance on how to design connection protection using these various materials, the materials I listed previously. Specifically, it explains how to design the protection in order to meet the code-specified design objectives associated with the engineering analysis option. And remember, that's the 250-degree average temperature rise at the interface criteria. Furthermore, TR10 contains examples and details to graphically show how to properly design the protection for some of the more common connection configurations. The details on this slide are from TR10, The one on the left shows one possible method of protecting an angle ledger connection between a CLT floor and a supporting CLT wall. And the detail on the right shows a design example of protection for a beam column connection using a concealed knife bearing plate. In all of these TR10 details and examples, only generic fasteners and connection hardware are used. And this was done on purpose to ensure that the details are generically applicable rather than being specific to a particular proprietary design or hardware make and model. TR10 specifies that the thermal separation time provided by wood protection can be determined by multiplying the calculated protection time, that's T sub P, by a factor of 0.85. For example, assuming the NBS specified nominal char rate of 1.5 inches per hour, if a single layer of wood having a thickness of 3 inches is used to protect fire or to provide fire protection to a wood member, the protection time, or TP, provided by this layer would be calculated as shown in this equation. In this example, it amounts to 141 minutes. That's the protection time. However, if this 3-inch thick layer of wood is used to protect a connection, then it also needs to provide thermal protection to limit the average temperature rise at the interface between the protection and the connection to 250 degrees or less. As noted above, the thermal separation time provided by this wood protection can be determined by multiplying the protection time by 0.85, and in this example, that would yield or provide a value of 120 minutes or 2 hours. So it works out so that in this example, that would meet your 2-hour fire resistance rating design requirement. TR10 also provides an approach for determining the thermal separation time that you would get from gypsum board protection. Specifically, the thermal separation time of gypsum board is taken as the non-combustible protection time multiplied by a factor of 0.5. So a single layer of 5/8 inch Type X gypsum board, which has an assigned non-combustible protection time of 40 minutes, would be assumed to provide a thermal separation time of 20 minutes. In this detail, you can see that clearly the single layer of 5/8 inch Type X gypsum board on the ceiling would not be sufficient to protect the connection hardware for the required 1-hour fire resistance rating time. In fact, it would only provide 20 minutes of thermal separation to the lower leg of that steel angle that you see where the blue arrow is pointing. Wherever multiple layers of protection are used, TR10 states that the 0.85 or 0.5 factor is only applicable to the layer that is immediately adjacent to the connection itself. This is true regardless of whether the thermal separation is being provided by wood protection, gypsum, or a combination of both. So in this example, which is similar to the previous one except it has 2 layers of gypsum board applied instead of just one, the 0.5 factor would only be applied to one of those layers. In other words, the layer adjacent to the connection would be assumed to provide a thermal separation time of 20 minutes, and then the other layer of 5/8 inch Type X gypsum board would be assumed to provide the full 40 minutes of thermal separation because it's not adjusted by the 0.5 factor. And so this would add up to a full hour of protection, 60 minutes, which meets the requirement in this particular example. TR10 also provides guidance on detailing wood members and protection to account for char contraction. Where the edges of wood elements abut, such as at the edge of a beam and column interface, the potential effects of char contraction should be evaluated. Now, let's define what we mean here by the term char contraction. First, we have to understand exactly what char depth is. Char depth is the distance between the location of the original wood surface prior to fire exposure and the location of the char front. And by the way, the char front is defined as the furthest extent of charring into the wood. As wood chars, its volume decreases such that the thickness of the char layer is less than the char depth. And this difference between the char depth and the thickness of the char layer is approximately 0.3 times the char depth at any given time. This phenomenon can result in the formation of a wedge-shaped gap, and you can see that in this example here, which propagates along the interface between two wood members. TR10 guidance indicates that ignition extends into these gaps at a distance that is approximately twice the char depth. As a result, additional wood cover or blocking is required to protect the area around abutting edges of wood members, and fasteners used to attach this protection are not required to be protected, by the way. This diagram depicts the profile of the char front in a floor-to-wall ledger connection when the steel angle hardware is properly protected. The char depth is labeled as A sub char, and the char's thickness is the width of the gray area that you see here. And you can see that the char front has formed a wedge-shaped gap at the interface between the wall and the 2x protection members. But because the protection has been designed to account for char contraction, this wedge-shaped gap does not quite reach all the way to the steel hardware. There's the wedge-shaped gap, and it doesn't quite reach that angle there, the steel angle. All right, we're almost done with this section. Before we wrap this section up, though, on fire protection of connections, I wanted to point out another newly added section in the IBC that pertains to connection protection, and that is section 110.3.5 of the IBC, which is pasted here. This was added to address the inspection of connection protection by code officials for the new mass timber construction types. These requirements are separate from and in addition to the special inspection requirements that we'll talk about in the next section of this webinar. And these inspections are to be made after the connection protection is installed, but before that protection is further concealed by any additional covers that may be applied for aesthetic purposes. All right, let's do another poll question here, Marcy.
Absolutely. Sorry, I had to move something. Materials acceptable for use in protecting connections in type 4A, 4B, and 4C construction include gypsum board, steel plates, additional wood cover applied over the connection, or answers A and C. Again, I am inclined to believe that people are listening, Jason.
Good.
Oh.
How many people have answered?
I have 70% of people have answered. So
okay. That's great.
Let's see. Let me share the answers. We have 93% say answers A and C. So
that's great. I think that's pretty much the same result we got in the morning session, and that is correct. It is the answer is D, which is both answers A and C. Gypsum board and additional wood cover can both be used for connection protection. Very good. All right, so now let's explore the code requirements regarding special inspection for these new mass timber construction types. The special inspection requirements for types 4A and 4B and 4C construction are contained in new section 1705.5.3 of the 2021 IBC. This section consists primarily of a table having the same number designation, which I'll show on the next slide. But before I show you that table, I wanted to stress that these provisions do not apply to traditional heavy timber, which of course, as you know, is now HT, type 4HT. They only apply to the three new mass timber construction types. Here's table 1705.5.3, which identifies each aspect of mass timber construction where special inspection is required. Generally speaking, these areas include anchorage to foundations, erection of mass timber construction, and various aspects of structural connections, including the fastener type and their placement and dimensions. The only connections warranting continuous special inspection are the quote-unquote adhesive anchors installed in horizontally or upwardly inclined orientation to resist sustained tension loads. This is basically what that means is adhesive anchors that are constantly loaded in withdrawal. And this is shown in item 3.2 of this table. And it's similar to table 1705.3, item 4A for precast concrete. So it's analogous to the same provision for precast concrete. And the reason for this requirement is for this requirement of continuous special inspection for this case is because of issues with adhesive creep under long-term tension loading. However, consistent with requirements for precast concrete, all other adhesive anchors that are not loaded in constant withdrawal loading need only be inspected periodically. And then also, all the other cases, even besides getting away from adhesive anchors, all the other cases were just periodic as well. Only periodic special inspection is necessary. And the reason for this is because most of the connections associated with the new mass timber elements, the mass timber elements in the new types of construction, that is, are similar to those that are used in traditional heavy timber. Hardware is similar, at least the generic hardware available out there. We're talking screws, bolts, etc. New section 703.9 of the IBC requires sealing of gaps between adjacent mass timber elements where those elements are required to be fire resistance rated. And then section 1705.19 provides for special or periodic special inspection of that sealant. However, there's an exception provided in section 703.9 to allow for the omission of sealant between adjacent mass timber elements. And specifically, this exception applies where standard fire testing has been performed to demonstrate that the assembly can still achieve the fire resistance rating without the sealant. So if it's tested without the sealant, then sealant's not required for that assembly. Special inspection of sealants between adjacent mass timber elements does not apply to joints as defined in IBC section 202. This is because joints, and specifically fire-resistant joint systems, have their own special inspection requirements in IBC section 1705.17. Joints are defined as having an opening that is designed to accommodate building tolerances or to allow independent movement. And the intersections of panels and members that are connected together do not meet this definition, at least not the typical cases we're talking about here. They don't meet this definition of a joint since they are rigidly connected and they do not have an opening. Now, none of these new special inspection requirements address mass timber structural elements that are considered to be fabricated items as defined in the IBC. Fabricated items, which can include mass timber structural elements, are addressed by IBC sections 1704.2.5 and 1704.251. These existing sections require either special inspection at the manufacturing plant or a quality assurance program audited by a third-party inspection agency. Existing section 1704.6 requires the owner of the or the owner's authorized agent to employ a registered design professional to perform structural observations during construction whenever certain criteria are met. These criteria include a trigger that kicks in for any structure that is considered a high-rise building. And of course, any structure in which the top floor is greater than 75 feet above fire department access is considered high-rise, so this would include the new mass timber construction types. However, I'll point out that this is not specific to the new mass timber construction types. It applies to any construction type that meets the triggers listed here. And I also wanted to note that this structural observation requirement does not waive the responsibility for the inspections that I mentioned in section 110, nor the special inspections in section 1705. In this last section, we're going to start here. I'm going to talk a little bit about sound transmission, and then I'm going to turn it over to my colleague Lauren Ross so he can tell us about energy performance. Of course, all of this pertains to mass timber construction specifically. Acoustical considerations for building designs are addressed in Chapter 12 of the IBC, along with other aspects related to the interior environment. Now, to be more precise, the acoustical considerations addressed in the IBC deal specifically with sound transmission through wall and floor ceiling assemblies that separate dwellings. There were no changes to IBC Chapter 12 specific to the new mass timber construction types. However, the existing provisions apply to all construction types. So that includes the new mass timber construction types. And thus, wall and floor ceiling assemblies in the new mass timber construction types will also be subject to the sound transmission provisions of IBC Section 1206. These provisions apply to wall and floor ceiling assemblies that separate dwelling units and sleeping units, or that separate such units from interior public areas, regardless of construction type. Assemblies like the ones that I just described must have a minimum sound transmission class, or STC rating, of 50. And this is a measure of airborne sound transmission loss. So the higher the STC, the more effective the assembly is at blocking sound transmission between adjacent dwellings. Airborne sound transmission, that is. And in the case of floor ceiling assemblies, there's also another requirement in addition to the STC. It's a minimum impact insulation class rating, or IIC rating, of 50 is required. Unlike STC, IIC is a measure of structure-borne sounds that are introduced directly into the building elements through contact, such as an object dropped onto the floor above or stomping feet. But again, the higher the IIC number, the more effective the assembly is at blocking those structure-borne sound transmissions from one dwelling to the next. Alternatively, such assemblies can be field tested, and there are separate standards that are referenced for field testing. They're different from the laboratory test standards, and you have different rating classifications if you take that alternate field testing route. And but those ratings would be the bar is a little bit lower for those. It's a rating of 45 rather than 50. And of course, the reason for that is because that acknowledges the fact that field tested assemblies, you're inevitably going to measure a little bit of flanking. And we'll talk a little bit more about flanking in a couple slides. So that'll introduce a little bit more sound transmission from the source to the receiving microphone in those field tests. Bare mass timber floor ceiling or wall assemblies are seldom used to separate dwelling units. And this is in large part because they typically cannot meet minimum STC and IIC requirements without additional components being added to them. Notice I said bare mass timber. That statement applies only to bare mass timber assemblies. And for example, a 5-ply CLT floor with a thickness of nearly 7 inches has an STC rating of 41 and an IIC rating of 25 if it's just a bare 5-ply CLT slab. So as such, components are typically added to one or both sides of the mass timber assembly in order to improve their STC and IIC ratings. This table shows acoustical properties of bare mass timber panels here. In construction types 4B and 4C, Exposed mass timber is often desired on the ceiling side of floor ceiling assemblies for aesthetic reasons. This means that any additional components necessary to achieve minimum specified sound ratings must be installed on the floor side or the top of the assembly. This is one of the main acoustical design distinctions between lightwood framing or lightwood frame floor ceiling assemblies and mass timber floor ceiling assemblies. In light frame construction, acoustical components are typically included both above and within and even below the assembly. For example, you have underlayment and or concrete topping above the framing. You have bad insulation between the framing members, and then typically you'll have resilient channels and gypsum board ceiling under the framing. That's not always so for mass timber, and hence there are some challenges sometimes for achieving the minimum required sound transmission classes. Now, there are three main ways to meet these challenges and to improve the acoustical performance of an assembly. First, you can add mass to the assembly. You can also add sound absorbing material, such as insulation, which I mentioned. And then you can also add decouplers, and any one or all three or any combination of these can be used. And that's the acoustical engineers are usually able to optimize and determine the best combination of these for improving and meeting the sound transmission design objectives. One of the characteristics of mass timber is that it has a high strength to weight ratio when compared to other panel and slab type construction materials. It weighs significantly less than, say, a concrete slab of the same thickness. With acoustics, more mass typically means better noise control. For comparison, a typical 6-inch thick concrete slab weighs approximately 80 pounds per square foot and has an STC rating of about 53, but a 7-inch thick CLT panel weighs about 18 pounds per square foot and would have an STC rating in the low 40s. That's if it's bare. Again, I'm talking bare panels here. A common way to improve acoustical performance of mass timber floor ceiling assemblies is to add a poured concrete or gypsum concrete topping layer on top of it. These cast-in-place toppings are usually in the range of 1 to 3 inches thick, and they serve to increase the mass of the assembly, thereby reducing sound transmission. Then also, decouplers are products that replace rigid connections with flexible connections along a sound transmission path from one side of an assembly to the other. This reduces the amount of noise that can directly travel through the structure, that is, from one side to the other. In mass timber floor ceiling systems, the most common decoupling products are underlayments and mats placed between the mass timber panel and the concrete or gypsum-based topping. The type and thickness of material varies by product, our product line and manufacturer, but the purpose is the same for these. It's to break the direct connection between the structure and the ceiling finish. Also, these serve to provide some sound absorption as well. And then another form of decoupler could be a sound clips on the ceiling side, either sound clips or resilient channels on the ceiling side to which gypsum wallboard could be attached. And one thing I wanted to point out in this slide, I won't reiterate it too much in the following slides because it's the same issue, but in some of these slides, you'll see this icon right here, type 4 HT. That's to acknowledge that some of these would not be permissible in type 4A or 4B or 4C because in certain cases, you'll see that there are concealed spaces in which there are combustible surfaces. they could be made to be compliant with type 4A, B, or C if, a non-combustible protection were applied to the combustible surfaces. All right, where the design calls for exposed mass timber on the ceiling, a common floor ceiling assembly includes the following from top to bottom, as shown in this figure. You see a finished flooring material. Then you see concrete gypsum-based topping, usually 1 to 3 inches thick. You have an acoustical mat or underlayment beneath that, and that's to provide that vibration break or decoupler. And then also you have the mass timber panel. Using a common 5-ply CLT floor panel, STC ratings in the range of 50 to 59 have been achieved for this common assembly buildup. IIC ratings are greatly influenced by the presence and type of finished flooring, and for this buildup, a resilient finished flooring material is typically needed to achieve IIC ratings of 50 or greater. Now, when certain floor coverings are applied over the concrete or gypsum-based topping, IIC ratings of 60 or greater are achievable, but this is usually only the case for floor coverings that are highly resilient or coupled with a resilient pad or underlayment. Probably the best example of that would be when you have a carpet and pad combination. Higher sound transmission ratings may be more easily achieved where there is no requirement for the mass timber ceiling to be exposed. For example, the installation of gypsum board on the ceiling can greatly improve STC and IIC values, especially when it's hung from resilient channels or resilient clip systems like shown here in this diagram. Although this conceals the mass timber panel from view on the ceiling, most of the mass timber surfaces in type 4B and all of the mass timber surfaces in type 4A for that matter are required to be protected with non-combustible protection anyway. And then also the spaces between the resilient channels or clips in such a system serve as a convenient location through which you can run mechanical, electrical, and plumbing services. And again, note that we have that type 4 HT icon here. That's because there is no non-combustible protection directly applied in this diagram anyway to the CLT, the underside of the CLT. That could be easily addressed by applying non-combustible protection, adding that in here, and the rest of this could stay the same. Mass timber panels can also be used for interior and exterior walls, both bearing and non-bearing. For interior walls, the need to conceal electrical and plumbing services is an added consideration. Common approaches include building a chase wall in front of the mass timber wall or installing gypsum board on resilient channels that are attached to the mass timber wall. As with bare mass timber floor panels, bare mass timber walls don't typically provide adequate noise control, and chase walls also function as acoustical improvements. So for example, a 3-ply CLT wall with a thickness of 3 inches, if it's just bare, it'll have an STC rating of in the low 30s, 33 for example. In contrast, this figure shows an interior CLT partition wall with chase walls on both sides, and this assembly would achieve an STC rating of 58, which of course exceeds the IBC acoustical requirements for multifamily construction. It should be noted, however, that again, this figure depicts an assembly in which there are combustibles within the concealed space, so that would not be permissible in types 4, A, B, and C. And again, that could be addressed fairly simply by replacing these these studs, these 2x3 studs with steel framing, and applying a non-combustible protection layer directly to the mass timber within the wall. All right, one way to minimize flanking paths, and I mentioned flanking very briefly earlier, it's a very important issue that needs to be addressed in acoustics. One way to minimize these paths for flanking, which is basically just another way of saying it's an alternate path for the sound transmission to propagate around the assembly in question, is to use various materials designed to seal air gaps and provide vibration isolation. The primary way to control flanking is to close all the air gaps. In the context of the three methods noted earlier for improving acoustical performance, vibration isolators can also act as decouplers. And with airtight connections, interfaces, and penetrations, a mass timber building can be designed and constructed to meet acoustic performance expectations. Several detailing and panel layout techniques exist that can help minimize flanking. As I mentioned earlier, a poured topping is common on mass timber floor panels. In fact, it's required in types 4A and 4B. So it's just a natural, easy way of of achieving your acoustical requirements as well. And by specifying a joint in the cast-in-place topping at dwelling separation walls, as illustrated in this figure, the designer can help to minimize flanking from one dwelling to the next as well. So let's see, I think I only have 14 minutes, and these slides are not actually part of the content of this presentation. So I'm going to skip forward to energy performance now. And Lauren, if you're ready, I'll give you. Sorry for encroaching on your time there.
No, you're doing great. You're doing great. So this is, I want to do, like Jason said, I'm going to be talking about the energy performance requirements of mass timber walls. And this goes well with the acoustics and the fire, just because we're talking about what additional things needs to be put on the mass timber, right? Whether it be insulation or whatever it may be to get the properties you need. Now, most of the design for energy efficiency for mass timber is going to be exactly the same as it is for any other building, right? It's not just because you're using mass timber doesn't mean that your lighting suddenly changes or anything like that. But what does have an impact is the opaque envelope section. And the IVC points to Chapter 13 for requirements, or the IVC Chapter 13 points to the IECC, International Energy Conservation Code, for its compliance. And that you can either use ASHRAE Standard 90.1 or some prescriptive design methods, and there's several of those, or performance design. Now, usually for your mass timber, if you're doing opaque envelope, you're looking at the walls. And they're either going to be the mass timber panels or curtain walls. Curtain walls are also very, very common. And those are going to be the same type of curtain walls that you would have designed for any other type of building. So we're just going to talk mostly about the opaque walls. Jason, could you advance for me? Perfect. Okay, so these are the code changes from the last code cycle that actually have kind of a big impact on mass timber design for energy efficiency. And I mean, technically, since there's performance and there's so much trade-off that's allowed in between various aspects of the building, that really almost any code change proposal you could argue it has an effect. But this is kind of the big one, and it's the U factor, which is a measurement of how much energy or heat or energy is allowed to go through the assembly. So the lower the number, the more stringent or tighter it needs to be. And you can see for above grade walls, there's two different categories there. There's the mass and then wood frame and other. And you'll notice that mass always has a larger number there. So if you're considered a mass wall, then you have more flexibility, design flexibility than if you have wood frame it for other. Okay, go ahead for advance. So the question is do you qualify as a mass wall? Now, the mass in energy for energy efficiency is a little different than just saying, hey, it's a mass timber building. You actually have to have the certain requirements of meeting a minimum heat capacity of 5 BTU per square foot per degree Fahrenheit. And that's going to be a measure. How thick the CLT or mass timber panel is going to have a huge impact on that. The same thing is whether you have layers of gypsum or other insulation, things like that can also have an impact. So this table right down here in the bottom right is showing that if you have additional layers of gypsum, then these are the minimum thickness you would need to reach that 5 BTU threshold. Now, this isn't including any other components that might be on there, like cladding or whatever it may be, but you'll see that generally speaking, you need to be in that 5 layers in order to be considered a mass wall. Next slide. Okay, so now we're pretending as if you've got the mass wall, right? Your whatever it is category you have, make it so you fit into the mass or whatever it is on your components, make it so you're a mass. How thick does the panel need to be in order to meet that U factor? Now, this is just assuming the mass timber wall and the layers of gypsum that you need for fire performance and things. So if this isn't any added insulation or anything else, and you can see that in certain areas, if you're considered a mass wall, then you don't need the 3-layer will be perfectly fine for you. That's where those red ones are circling. But you see, if you go up to 7 layers, then a lot of the climate zones can be met with that. And next slide. And this is probably actually a little bit more helpful. This is saying, okay, this is specifically, I think, a 3-layer, but if we're able to say a 3-layer system is considered a mass wall, which is atypical, but for whatever reason, we can say that how much additional insulation is needed in order to meet the U factors. And those red squares are saying that, hey, look, through all the climate zones 1 through 7, if you have an R9 mineral wool, you're good. Okay. Next slide. And then, but if you're a non-mass wall of 3, which is much more common, I think, then you're going to have a much smaller area that you can R9 works, and that's shown by the smaller squares in this. So this case, you can only go up to climate zone 4. Next slide. So this is a mass wall so this is comparing against the last one where we said, hey, look, if you're a 3-panel CLT, you're probably not mass, and so you're gonna need some insulation. This is saying, hey, if I make my CLT a little bit thicker, 1 layer thicker, how much insulation do I need then? And those blue squares are where technically you wouldn't need any insulation to meet the energy requirements. So it becomes a trade-off. If you want to have a little bit extra panel and thus can have less or no insulation depending on climate zone and whatnot, and so it's the cost of the panel versus cost of having an extra trade go in there and for the insulation. Next slide. So this is what that's showing right here is a typical 5-layer CLT panel exterior wall. You're going to not need insulation in climate zones 1 through 4 because you should have at least 1 layer of gypsum just for fire performance. Next slide. Versus this, where this is saying, hey, look, I've got a 3-layer, and so I'm probably not going to be considered mass. And then you'll see the additional R value required is basically an R9 mineral wool for most places. So if you have a 3-layer, you're going to have R9 mineral wool. If you have a 5-layer, you're not going to need you don't need to have mineral wool. And so that's showing the trade-off options there. Next slide. Oh, here's the poll question.
All right, do we have time for this real quick? Let's try it real quick.
Mm-hmm.
All right, so a 3-layer 4.125-inch CLT wall with 2 layers of gypsum requires insulation in all climate zones to meet minimum U factors. Ooh, this is a little tricky.
This one's a tricky one because it really depends on whether that 3 layers is considered a mass or not. In this case, I'm saying it's not mass, so it's going to have a higher. I'm assuming it's going to not be mass, so it's going to be a higher level of performance.
Okay. And just remember, everybody, this does not impact your CEUs at all. So let's see, I've got almost 70%. Let's close and share. So 53% true, 47% false. And I think that is right on the money what we had this morning. So
yep, that's good. That's good. And I think that concludes the presentation.
Oh, wait, did you say what the answer was?
Oh, it's true is the truth. So I think that's, yeah, the 53% or whatever it was, the majority had it.
Do you want me to go back, Lauren, to show that?
No, it's okay. It's okay. It's a kind of a tricky question because it's not talking. It doesn't really say whether it's considered a mass wall or not. But okay, next slide for me, would you, Jason?
Right. Yeah.
That's the conclusion. But there's a couple resources I also want to talk about real quick. There's AWC and ICC publication on mass timber and the requirements and the code changes and all those things that are really handy and great. It kind of goes into more detail in different aspects of it. And next slide. And the ICC has an exam now to get you certified to be a special inspector for mass timber, and you can find information on that at just the ICC's website, iccsafe.org. And I think that's it. It's just questions now.
All right. So I am going to go ahead and close real quickly, but if you came on late, please be sure to stay for the question and answer so that you make sure that you get your time, the hour and 21 minutes at least. So thank you. I'm going to actually take the sharing so that I can show my slides. I just have 2 slides for you really quick. Thank you, Jason. Thank you, Lauren. Our partner organization, Woodworks, provides wood project assistance and other resources. If you want to reach out to them, email help@woodworks.org or visit their website at woodworks.org/project-assistance. Or you can also request assistance from them on our survey. We have one question there that you can put your information in to get contacted by them. And then code official connections. If you're a code or fire official, go to our website and check out our free program for individuals employed by governmental jurisdictions. And that's all I've got. I also have this reminder slide with some information that I will keep up as you are filtering out so that you can jot things down. I will give you back to Jason's slides. So while you are going through question and answers, he might want to refer to some of his slides.
All right, thanks, Marcy. We've had a lot of questions come in. Thank you, everybody, for your participation. So we'll go ahead and ask a few right here. So Jason, the first question that came in, so actually I was expecting lots and lots of questions about CLT, which we did get, but this one is actually about glulam. And since that is considered a mass timber product, I thought it would be good to give it a little bit of love. So when we're dealing with glulams that are going to be fire rated, I know you had that slide early in the presentation that showed when we replace some of our interior laminations with high tension laminations for fire ratings. What do engineers need to show on the structural drawings to determine these glue laminations that we need to replace? Would we refer to the size of the glue lam section that we would be specifying out of the NDS supplement, or would we need to specify, you know, substitute 2 laminations for this beam? Can you give us a little guidance on what folks should look for?
Yeah, the guidance is given in section 16.2.4 of the NDS. That's in chapter 16, of course, which is the fire design chapter of the NDS, and it does it states basically what you said, that you know, if you need to achieve a 1 hour fire endurance or fire resistance rating, then you replace 1 outer tension lamination for a core lamination, and then for 1.5 and 2 hour fire resistance ratings, you would do 2 outer tension laminations for 2 of the core laminations. So yeah, that's what would need to be specified, and just reference that section of the NDS, you know, and state the fire resistance rating requirement.
And also, we do encourage folks, you know, have a conversation with your glue lam supplier if you're not sure. You know, it doesn't hurt to pick up the phone and talk to the folks that are manufacturing it and tell them what you need, just to get everyone on the same page. Yeah,
communication, as I mentioned in one of those slides, it does require communication with the manufacturer in that particular case, because it's got to be manufactured a certain way to achieve that fire resistance rating. And but the you know, if it's specified as specified in accordance with 16.2.4 of the NDS, the manufacturer, the glue lam manufacturer, should know exactly what to do with that. Yep.
Great. Here's a question about fire resistance of connections. If we're dealing with bolts, we have bolt heads, right? Do those bolt heads that are exposed need to be protected for the fire rating of the connection?
Yes, yeah. Every part of the fasteners and every part of the connection hardware would need to be protected, such that no part of it, none of those steel or whatever the material may be, portions of the connection are heated or receive a temperature rise of greater than 250 or greater. So in other words, they need to be limited to that 250 degree Fahrenheit temperature rise criterion.
And oftentimes I've seen that protection achieved where they'll kind of recess out the area around the head of the bolt and then provide like a wood plug or other cover on the outside.
Now I did mention very briefly during my presentation that the fasteners that are used to attach the protection, that does not need to be protected, and that's that is stated in TR10, because obviously it'd be just about impossible to do that for the protection fasteners, you know. But I think the question was regarding the structural hardware, the hardware that's used to transmit loads within that connection. And if that's what the question was referring to, then the answer is yes. Every part of that connector, every part of that bolt needs to be protected for the full fire resistance rating time.
Yeah. Here's an interesting question. You talked about that gap char calculation. Someone wants to know, can we substitute fire caulking in lieu of that gap char calculation?
There's no prescriptive means of doing that, other than, well, I mean, there is a prescriptive means, and that is as an alternate approved material, you know, but there's no prescribed time assigned to any fire resist or intumescent fire caulk. because of course those are proprietary formulations, and performance varies from manufacturer to manufacturer and from product to product. So the answer is, in general, no. However, there are ways of demonstrating that if you use those in lieu of a wood collar, or something like that, if it serves the same, if it meets the same design objectives, then there's a way of getting that approved and showing compliance. But generally speaking, that requires testing to demonstrate.
Right.
Either on the part of for the particular project at hand, or on the part of the manufacturer of the sealant, the caulk, the fire caulk. Yeah.
Great. We were talking about sound transmission and how increasing the mass of an assembly can benefit the acoustic performance. So we often do that with mass timber assemblies by adding that layer of gypcrete or lightweight concrete topping on top of the floor slab. Someone had a question: can this affect the vibration performance of the floor? And are there any vibration controls or requirements that are out there that we could point folks to?
Yes, there are resources available. Yes, it does affect. It would affect vibration, because obviously if you're increasing the mass without significantly increasing the stiffness, if you're obviously, the vibration is a function of both mass span and the stiffness, and so you will, by adding mass without proportionally increasing the stiffness, then you're going to wind up decreasing the natural frequency, of that span. And so yes, that could bring you down into the range of frequencies, of vibration frequencies, that is considered annoying from a human factors standpoint. So and yes, there are resources available for addressing that, for addressing the vibration.
Yeah, I believe the US CLT handbook has a chapter on it.
That's right. Yeah, CLT handbook is one of those. Yeah. But yeah, that is a good point, that adding that mass, while that it improves sound transmission loss, it also could bring you, not necessarily, but it could bring you down into the range, the frequency range that's considered annoying, for annoying vibrations. Yeah.
Right. All right. One last question. Intumescent paint. What's the story? Can we use intumescent paint for protecting exposed metal connectors and timber connections? Is that something that's in the code?
Yes and no. It's not explicitly recognized as having, because of course, what do you mean by intumescent paint? Because those are all proprietary. There's nothing, there's no standard intumescent paint, at least not with a recognized contribution to fire resistance ratings within the code, at least not like we have for a gypsum board, for type X gypsum board. So in that respect, no. In that respect, it's not. But then it is, in a roundabout way, it's recognized in the code as, or in the NDS, that is. Remember where I mentioned that you can have other approved materials like coatings or insulation, where a fire resistance contribution has been demonstrated. And again, it goes back to, that's going to require testing to demonstrate that. So that would fall under the other approved materials category in section 16.3 of the NDS.
All right, great.